The Hardy-Weinberg equation provides a mathematical equation that can be used to calculate the frequencies of the alleles of a particular gene in a population. Therefore, by using this equation here, the Hardy-Weinberg equation, we can calculate allelic frequencies. So to understand this, it's better if we give some example. So imagine like we have two alleles, allele A, capital 1, and allele A, the recessive one. This one stands for brown eyes, okay, and the recessive stands for blue eyes. So imagine in this population, we only have these two alleles. If we have more than two alleles in a population, then the Hardy-Weinberg equation cannot be used. So if we're talking about multiple alleles for a gene, then we cannot apply this equation. In Hardy-Weinberg equation, we symbolize the dominant allele with the letter P and the recessive allele with the letter Q. So inside a population, if we add all the dominant alleles, P, with all the recessive alleles plus Q, is going to give us 1, or if you like, 100%. So why 100%? Because these are the two alleles that we have, so we expect if we have a population of 100 people, for example, if we add them up, then it's going to give us 100%. To apply the Hardy-Weinberg equation, we need to assume that 5 conditions are met. What do we mean by that? There are 5 conditions that need to happen in order for Hardy-Weinberg equation to be applied and to be valid. For example, no mutation arise, because if we have a mutation, then we are going to have new alleles. Therefore, our calculations for allelic frequencies will not be valid. Then, the population must also be isolated. Again, it's for the same reason as the previous one, so we don't get new alleles in our population. Number 3, there is no selection, because if we start favoring specific alleles, then we are going to affect the frequencies, so we don't want that. Number 4, the population must be large. And number 5, mating within the population must be random. Why is that? Because if we start doing selective breeding, for example, then it means that we are favoring specific alleles, so at the end, the frequencies are going to change. So if all these 5 criteria are met, then we can have a valid calculation for allelic frequencies by doing the Hardy-Weinberg equation. So again, let's take these two genes that I showed before. This one stands for brown eyes, and this one here stands for blue eyes. And I wrote one equation. I also said that this one is going to be symbolized with the P. We always symbolize the capital, the dominant allele with the P, and the recessive allele with the Q, and I said that P plus Q equals to 1. Now these two alleles can be combined together in 4 different ways. We can have homozygous dominant, we can have heterozygous in this way or in this way, or we can have homozygous recessive. Since the dominant allele is symbolized with P, we are going to show this as P squared. Okay, now this one here it's going to be PQ, this one here again PQ, and this one here is going to be Q squared. And we can use these letters to also represent the genotypes. So if we have these genotypes, then someone is P squared. If they have these genotypes heterozygous, then it's PQ, and if they are homozygous recessive, then it's Q squared. We can add them up, and we can say that P squared plus 2PQ plus Q squared equals to 1. This here is the Hardy-Weinberg equation. So in this video we saw 2 different equations. First the Hardy-Weinberg equation and also this equation here. So I explained the theory behind the Hardy-Weinberg equations. In the next video I will show you application of the Hardy-Weinberg equation.